Okay. So we're going to introduce really basic, concept today with electricity. Okay. We're going to start with something called the Coulomb. Now, did you guys talk about that in grade 11? You sure? I think we did. All right. Now, the Coulomb is defined by the amount of charge, and this is actually related to the experiment you're going to do on Friday, okay? Because at some point, someone had to make a discovery and determine how much charge does an electron or proton carry, okay? So a Coulomb is a particular amount of charge that is carried by, and here's the number right here, okay? 6 times 10 to the 18 electrons or protons. Now we know from grade 9 or 10 that electrons have a charge, right? And in chemistry you write it as an electron is negative what? Negative 1. But negative 1 means it's just an arbitrary number, okay? And a proton has a charge of what? Plus 1. And a neutron has a charge of plus what? Very good. No charge, 0, okay? Very good. Now, in terms of the amount of charge of one electron or proton, it's actually measured to a particular value. The experiment that you're going to conduct on Friday is actually going to show you how that was determined, okay? So can I just show you that experiment really quickly? I'm going to come back to this, okay? So we're going to be doing an experiment. It's called the Milliken oil drop experiment. Okay. Basically, the idea is this is an experiment was done where these oil drops were measured in an electrical field. Okay. Now, electrical field is again an area of where there is a force that's being generated by electricity. That's either going to be attractive or repulsive. So you have these particles. And so we're going to spray, okay? And you can see these are little oil droplets, right? And you can see that right now they're just moving from one side to the other side, okay? And now this animation, I know that looks like they're moving up, but they would be moving towards the surface of the Earth, right? Because gravity would be the only thing that would pull them down. What we're going to do is we're going to figure out a way to trap them. So if we, for example, increase the voltage, oh, we don't have the voltage on. You'll notice now something happened, right? You notice initially all the particles are moving. So if I spray, so all these little droplets, right? And they're moving, in this case, they're moving in the direction of the gravitational field, which is towards the center of the Earth. But if we turn on the voltage, in other words, we run a current through this system, we can see that now things are moving the other way, right? What may happen though is you may actually end up trapping an oil droplet, okay? Now, okay, in this case, it's not actually perfectly trapped. What you might want to, no, not what you might want to. What you're going to try to do is you're going to try to play around with the voltage to the point where we can actually trap that oil droplet so that it stops moving. Now here's the thing. I want you to think about this, okay? If we have gravity, which is pulling the oil droplet one way, and then we turn the voltage on and we have electricity that's generating a force, and the oil droplet stops moving, what does it tell you about the force down and the force up? It's equal, right? So we're going to be exploring this experiment. I'll talk more about it tomorrow. But this is the experiment that was done to determine the strength of that electrical force, which was then used to determine the amount of charge, basically that was carried by an electron or proton. Okay? So we'll talk more about this tomorrow. Okay, so here's what we know. We know that we know electrons and protons have a charge. Okay. We know that each proton electron has this particular amount of charge, which was discovered using that experiment that I just showed you. But we'll investigate that more in detail tomorrow, okay? Now, what we could do is we could figure out the force of attraction or repulsion between things that are charged, just like we did with gravity. You'll notice the equation right here, and I just cut and paste this equation. But you'll notice something about the equation that determines the force of attraction or repulsion. This could be repulsive force, okay, between two charged objects. Here's the thing. It's the function of a constant, which is called K, times the amount of charge of one thing times the amount of charge of another thing divided by the distance between them squared. Where have you seen that equation before? It's exactly the same as the Fg equals G m1 m2 over r squared. It's the same equation. Obviously not the same thing, but it's the same format. Now K is a constant, okay, do I have it here, the constant? No, I don't have it here. Now K is a constant, and I'm actually having trouble remembering. I think it's 9 times 10 to the 9. But let me just pause the video and just double check that. Okay, yeah, so double check because I couldn't really remember. Yeah, so K is this number. Okay, I'll show you the number in a second. It is, so K, this constant, is actually 9 times 10 to the 9 Newton meter squared per Coulomb squared. Now remember, Coulomb is the amount of charge, okay? The amount of charge of a proton or number of protons or electrons. You'll notice in this equation then, this is the equation for force, right? Now this is the electrical force. What's the unit for force? Newton, right? So Q represents the amount of Coulomb of one charge or one thing. So you have Q times Q, that would be Coulomb squared. And then R is in distance, is in meters, so that would be meter squared. So what would cancel out then would be the meter squared and the c squared. The c is not the speed of light, okay? It's the amount of charge squared. You'll be left with newtons. Now I want you to know something. You guys study the fundamental forces in grade 11, the 4 different types of fundamental force that we see in the universe. There's the force that holds the nucleus together. That's called the strong force. There's the force that causes the nucleus to change. So in the video that you saw, which I'm going to refer to a lot, remember they were looking at the atomic nuclei of uranium, and it was undergoing decay. The force that causes the change of the nucleus is called the weak force. Then we have gravity, and then we have the electromagnetic force, which is what we're looking at now. This is the electromagnetic force. Of the 4, the weakest is gravity. Electromagnetism is stronger than gravity, but weaker than the strong force. Now, here's the thing. How do you know it's stronger than gravity? Well, what was the constant for the equation for big G? What's that value? It's really tiny, right? What is it? 6 times 10 to the negative 11. Look at this constant. It's 9 times 10 to the 9. So in terms of magnitude, it's like 10 to the 20 times bigger. And that makes a lot of sense, because think of it this way. What's holding you up right now is the electromagnetic force. You're sitting on your chair, and it's the repulsion between the electromagnetic force in the chair and you that's holding you up. And that's basically battling all of the Earth. The entire Earth is trying to pull you down to its core, and you have this little chair that's holding you up. And you can see why that works, because the electromagnetic force is just way stronger than the gravitational force. Okay? Okay, so let's look at using this equation. Because, we've talked about force a lot. Let's use this equation in this first example, okay? So actually I need to give myself a little bit of space here. Okay? And then I'll give myself a bit more space over here. So we'll just do 3 pretty simple questions, okay? So we'll look at this one, okay? How much force is acting on it? So how many of you have ever played around with the balloon? You've rubbed it on your hair and you stuck it to a wall. What's holding the balloon up? Electromagnetic force, right? It's the force of attraction between the balloon and the wall in that case. What's pulling it down? Gravity. If it's just stuck in the wall, that means that the two must be what? Two must be balanced. Okay. So, let's figure out if we can calculate the amount of force. Okay. So, what is the force acting on a charged balloon if they each have, charged balloons, on a charged balloons. I need to go to English class, ladies. Yeah. So we have 2 charged balloons. Imagine we have 2 charged balloons. Okay. All right. And they are separated by a distance of 50 centimeters. But remember, the distance has to be in what? Meters. Okay. The distance has to be in meters. So D is 0.5 meters. All right. Now, each balloon has a charge of 1 nanocoulomb. Okay, what's a nanocoulomb? Very good. So a nanocoulomb would be 1, so Q would be 1 times 10 to the negative 9. Okay. So what would the force of attraction be? We're going to assume it's an attractive force. It could be a repulsive force. Actually, most likely it will be a repulsive force. I'm assuming it's the same balloon or material. So you guys know how that whole static electricity works, right? You rub the balloon on your hair, and what happens is a transfer of electrons. And I can't remember if the balloon becomes positively charged or the hair becomes positively charged. But in either case, the balloons should have the same charge. So you would expect that there's going to be a repulsive force. So we can measure that force because the equation is K, which is 9 times 10 to the 9, times Q1. So we'll call this Q1, which is 1 times 10 to the negative 9, times Q2, which is the same, 1 times 10 to the negative 9. And that will be, well, that's a really awful line. That will be over that will be over 0.5 meters squared. Okay. That should be a capital E. Alright, so 1 times 10 to the negative 9 squared is 1 times 10 to the negative 18. So that would be 9 times 10 to the negative 9 on top over 0.25. That should be 3.6 times 10 to the negative 8 newtons. If I did my math correctly. So that's the attractive, or actually in this case, I'm going to assume it's the repulsive force. Okay. Okay. Easy so far? It's pretty much the same equation for gravity, but obviously it means something different. Okay, Emily checking it out, double checking the math. Is it okay? All right. Okay, let's look at another example. An electron is placed between 2 positively charged objects. So it is 20 centimeters from a 3 microcoulomb object and 45 centimeters from a 10 microcoulomb object. So we can visualize it like this. So here is one object. Here is the other object. And we have an electron in the middle that's negatively charged. I shouldn't have really drawn it in the middle. It was actually closer to one side. So let me make sure we visualize this correctly. Okay. So it's 20 centimeters from a, so imagine this is the one that's 3 microcoulombs. So microcoulombs. And this one, that's a symbol for micro. And 10 microcoulombs. Okay. The electron is closer to the 3 microcoulombs. This is right over here. Okay, so this distance is 0.2 meters. Remember, it's got to be in meters. And this distance is 0.45 meters. That's why I failed art school, because I can't scale things properly anymore. See? Okay, so here's the thing. If you think about from the point of view of the electron, right? There will be an attractive force which way? To the left, but also to the right. Because this object will attract the electron this way, but then this object will attract the electron this way. So we got to think of this as something like you would have saw in grade 11. You have an object in the middle, two things are pulling at it. Which way does it go? What would you do? What would you do if you want to know which way something would move? And you have two forces on either side, pulling in the opposite direction. What would you calculate? The net force. Very good. Okay? So we're going to figure out what the net force is. So let's look at this side. We'll call this the left side, and we'll look at the right side, okay? Now, it's an attractive force. So on the left side, it will pull to the left, and on the right side, it will pull to the right. Does that make sense? If it was a repulsive force, in other words, if this was an electron, and this was an electron, which way would the force point? It would point to the right on this side, because this electron is not going to be attracted to another electron. It's going to be repelled by it. So you got to know which way the force vector is pointing. Okay? You have to know that. In this case, it's pointing towards the positive object. So what we can do is on this side, we can figure out the force of attraction. And we could use that equation again. We could use K, Q1, Q2 over R squared. And we can figure out on the left side, what is the force of attraction? So K is 9 times 10 to the 9. Q1, so one object is 3 microcoulombs. What's a micro? 10 to the what? Yeah, very good. It's 3 times 10 to the negative 6. Now, Q1 would be this positive source. Q2 would have to be then the electron. Right? Has to be the electron. So what's the charge of one electron? What did we define it as? 1.6 times 10 to the negative 19. A very, very tiny amount. Okay, and then we could draw a line here. Wow, it's really bad. And the distance between the two is 20 centimeters or 0.2 meters squared. Okay, that's the left side. So we can figure out what that force is. Right? So just by looking at it, it should be like, this is what, 4.8 close to 5 times 10 to the negative 25. That's like 45 times 10 to the 16, negative 16 divided by 0.04. So you're looking at a number that's really, really tiny. It's probably like 10 to the negative 14. What'd you get? What's your number? Okay, negative 13. Okay, so 1.8? Okay, we'll just say 1.1 times 10 to the negative 13, right? Okay, now we'll do the exact same thing on the other side. The force is going to be, well, it's K. K is constant. Now Q1, the source is not 3 microcoulombs, the source is 10 microcoulombs. So it's 10 times 10 to the negative 6. But it's still the same electron, right? So it's still 1.6 times 10 to the negative 19. The distance is different though. Even though this Q has a bigger charge, it's further away though, right? So the distance between the electron and that source is 45 centimeters, or 0.45 meters. So what would the force be on that side? Sorry, what was that? Okay, so it's same magnitude as the other one, but it's not the exact same, right? So which way will that electron move then? To the which way, right or left? So on the right side we have 7.1. On the left side we have 1.1. So the net force then would be just the sum of those two, right? The net force would be 7.1 times 10 to the negative 13 minus 1.1 times 10 to the negative 13. So the net force in this case would have to be just simply, oh, this is to the negative 14? Okay. So then that changes everything. So the bigger force of attraction is on the left side, right? So then the net force would be this minus this. So what would that be? Let's do like 0.4 times 10 to the negative 13, or 4 times 10 to the negative 14, I believe. Probably around. Let's do that. What you got? So 1.1 times 10 to the negative 13 is the same as 11 times 10 to the negative 14. So that's about 4. About 4 times 10 to the negative 14. Okay. So the net force is 4 times 10 to the negative 14 to the left. So we expect the electron to start moving to the left. Okay. All right. One more question. So here's the thing. Does this look any different then? Like, think about it. It's still net force. It's a very similar equation to what we use with gravity. Same format, right? Everything's the same. The only difference is we could have repulsive forces. And I think that's the next one. Oh, it's not the next one. I thought it was the next one. Okay, so I don't have an example of a repulsive force. Maybe I should just talk about it then. Okay, I'm gonna, and we will deal with this, okay? But I'm gonna ask you a question. If we had not a positive charge here, but we had a negative charge, okay? What if this question, because everything's the same, okay? What if this question said, okay, we have a 10 microcoulomb object, but it's negatively charged, okay? Now, the numbers would still be the same, right? It still will give you the exact same value. So on the left side, everything is the same, and we figured out that it was 1.1 times 10 to the negative 13. Now, on the left side, we figured out it was 7.1 times 10 to the negative 14, right? Everything's the same, but what changes though? What's that? The direction. So this pulls the electron to the left. What would this do? Instead of pulling to the right, if this is negatively charged, this would pull to the left. Or I should say not pull, but push it. Right? So in that case, the net force would not be the difference between the two. It would be the sum. So that would be the only thing that I think might give you a little bit of trouble, because the equation's the same, but you got to consider with gravity, it's always an attractive force, right? Here, it could be a repulsive force. So just keep that in the back of your mind. Which way is the force pointing? Okay? So that could be a little bit trickier. Okay, last question then. And then tomorrow we'll talk about the electric field and what it actually looks like, okay? Alright, so we have an object here. So we have an object that is exerting a force, okay? I don't know what the object is, but it's exerting a force. And so imagine that this is my object. This rectangle represents my object, and it's positively charged, okay? And there's an electron that's floating in air, and this is the ground, okay? Now the electron is balanced, so it's not moving down, it's not moving up. So what does that tell us about this versus this? Now, here's the thing. If this is positively charged, the electron is going to be attracted to it, right? But the electron is also going to be attracted to the ground because of gravity. So, what does it tell you about this? What does it tell you about the electric force? And what does it tell you about the force due to gravity? If it's perfectly balanced, it must be what? Very good. Must be the same. So, question is, how far from a 1 nanocoulomb charge would we need to place an object, like an electron, so that it would be stable? Okay? We already know what so here's the thing. In this case here, what we could use is the weight of the electron. I would not recommend using, for this question, I would not recommend using this equation. Why not? Why wouldn't you use that one? Well, that would be, the M1 would be the electron, the M2 would be what? The Earth. But what we don't know is, we don't know what R2 is, right? So, but we know that this equation really just gives you, like on the surface of the Earth, it just gives you your weights. So we could just simply use this equation, mg, right? So what we could say is, we know Fg equals Fe, so we can do this. We can say Fg equals Fe. Well, Fg is mg, and Fe is K Q1 Q2 over R squared, right? And we can now set them equal to each other. We're looking for R, so what we can do is we could say, okay, well, R has to be then K Q1 Q2 over mg. Yes, square root of that. Okay, so let's figure that out. So K is 9 times 10 to the 9. That's just a constant. Q1, well, the source is 1 nanocoulomb. 1 times 10 to the negative 9. We're holding up an electron, which is 1 times 10 to the it's 1.6. Not 1. Erase. Okay. it's 1.6 times 10 to the negative 19. Okay. And that's over mg. Now the mass of an electron is given. You see it's really tiny. 9.1 times 10 to the negative 31. That's a very tiny amount of mass. Times g, which is 9.8. All right. So, a lot of numbers here. And a lot of big numbers in terms of the numbers themselves are small, but, you're dealing with large exponents, like 10 to the negative 31. These are big numbers to manipulate. So here's the thing. 9 times 10 to the 9 and 1 times 10 to the negative 9 cancel out pretty much, right? That leaves you with what? Should be just 9. Right? So then we have 9 times 1.6 times 10 to the negative. Can you see that? This is supposed to be negative 19. Sorry. Not negative 9. So you're left with about 9 times 1.6 to the negative 19 over 9.1 to the negative 31. So we can cancel the 9s. Alright, forget it. I can't do this in my head. I'm getting dizzy doing this in my head. I don't feel up to it right now. What's the answer? What do you got? How much? $400. Well, here, this is going to cancel out. So that uses, and then here we could do, so that's 10, that's going to cancel out. So that leaves the 1.6 divided by 10, which would be basically to the negative 20. So it's 1.6 to the negative 20 divided by 10 to the negative 31. So it's going to be like, that will give you 1.6 times 10 to the 11. So then the square root of that would be so that's about, that's right, because that would be 4 times about 10 to the 5, right? And 4 times 10 to the 5 squared would be 1.6 times 10 to the 11. Yeah, that's fine. So that's 400,000 meters. Or I just rounded it off, okay? So 400,000 meters. So just think about that for a second, okay? You have this object that is 400 kilometers away, 400 kilometers away from a source object that's being held up against the entire Earth, trying to pull the electron down. Just a reminder how much stronger the force of attraction in terms of electromagnetism is versus gravity. So that's the introduction. We looked at the force of attraction using that equation K, Q1, Q2 over R squared. Tomorrow we'll talk more about electromagnetism. Okay, ladies, that is it.